Welcome to my video course on mastering ERTMS/ETCS signaling systems. Today we're going to establish a really solid foundation on exactly how Europe transformed its completely fragmented rail networks into an absolute modern, unified engineering marvel. We'll be diving right into an introduction to ERTMS, why Europe so desperately needed it, and the fascinating journey of European railway integration.
Okay, here's our agenda for today's explainer. First, the evolution of train protection. Second, Europe's interoperability challenge. Third, the ERTMS standard solution. Fourth, the ETCS and GSM-R subsystems. And finally, the advantages of unified railways. Let's get right into it.
Section 1. The evolution of train protection. To truly grasp modern railway tech, and why Europe actually needed a totally new approach, we first have to look back at how train protection has evolved over the past century or so. Back in the day, around 1850, it was all early steam engines. Moving into the 1900s and 1930s, networks relied heavily on fixed trackside signals. Think of those literal green and red lights on poles telling the driver what to do. But here's the catch. As trains got much faster, human reaction time became a massive bottleneck. That brings us up to 1980, with the introduction of early ATP systems, and then finally the highly advanced ERTMS-equipped trains of the 21st century.
So the absolutely crucial point here is understanding this ATP baseline. In the 1980s, rail signaling systems were introduced to constantly monitor the speed of the train. An ATP system is essentially designed to step in as an automated safety net. It uses target speed indications, audible warnings, and, here's the kicker, it automatically applies the brakes if the human driver happens to miss a red danger signal. It was a massive, game-changing leap forward for railway safety.
Section 2. Europe's Interoperability Challenge.
Now, while those national ATP systems were incredibly effective, different countries basically rushed to build their own proprietary versions. The result? A chaotic, messy patchwork of over 30 completely different, mostly incompatible national signaling systems scattered across the European map. You've got AWS in the UK and Ireland, NDusty over in Germany, TVM in France, ASFA in Spain, the list just goes on. Every single system was built to completely different national requirements and operating rules.
You can just imagine the absolute logistical nightmare this caused for cross-border traffic, right? Because these systems quite literally couldn't talk to each other. A train traveling from France to Germany couldn't just seamlessly cross the border. No way. It required insanely costly physical modifications to the trains just to support multiple systems, or the crews literally had to perform complete train or locomotive swaps at the border just to pass from one country to another. It heavily impeded the free movement of international rail traffic.
Which brings us to Section 3, the ERTMS standard solution.
With the push for European integration, there was a desperate, urgent need to establish common rules to sort out this chaos. Following some big decisions made back in 1989, a project was launched to build a common, interoperable platform, and that's where ERTMS, the European Railway Traffic Management System, comes in. It was chosen as the ultimate international command, control, and signaling system. It basically takes all those messy legacy systems and substitutes them with one unique integrated framework. It establishes common rules for the seamless free movement of rail networks across all European countries.
Now, a major paradigm shift with ERTMS is its use of something called cab signaling. What this means is that basically all the commands for the driver are displayed directly on digital screens right inside the train's cabin. This brilliant piece of design makes those conventional fixed trackside signals completely obsolete. By shifting the functionality and safety responsibilities from the physical infrastructure straight into the vehicle's onboard software, rail operators save a massive amount of money and time on trackside installation and maintenance.
Section 4. ETCS and GSM-R subsystems. Okay, so to make this unified cab signaling system actually work in the real world, the ERTMS program basically combines two highly specialized elements. Simply put, ETCS, the European Train Control System, acts as the brain. It handles all the complex signaling, the safety controls, and the automatic train protection. Meanwhile, GSM-R acts as the voice. It's the international wireless communication standard that guarantees a highly secure, constant data exchange between the moving train and the trackside control centers.
This brings us to a really fascinating concept, the safe braking model. This mathematically visualizes exactly how the ETCS subsystem acts as a hyper-advanced ATP system to supervise train speed in real time.
It creates this downward curve, transitioning smoothly from the maximum speed down to the granting speed as the train approaches a target point, like a stop signal.
The system is incredibly strict and follows 3 core steps to keep everyone safe. First up, it calculates and draws that protection curve instant by instant, based on the train's exact characteristics and the track ahead. Second, it's constantly verifying that the train's current speed stays safely below that model's maximum limit. And third, if the train does happen to travel faster than the maximum allowed speed, the system automatically steps in and applies the brakes to slow it down. It ensures the train never, ever breaches that ultimate safety threshold, basically completely removing human error from the equation.
Section 5. Advantages of unified railways. Having looked at the technical architecture and those core braking mechanics, let's look at the tangible operational benefits here. Because beyond just fixing that massive border crossing headache, ERTMS drastically increases railway performance across 5 key areas. First is safety, thanks to that continuous speed supervision we just explored. Second is capacity. Operating trains closer together safely can actually yield more than twice the capacity of a conventional line, which is huge. Third is accessibility, since there are fewer physical track magnets and cables to worry about. Fourth is interoperability, giving us those seamless, uniform interfaces across borders. And finally, maintenance. It creates a highly competitive market with standardized parts from multiple suppliers and way fewer critical safety interfaces to constantly check.
And really, this is the ultimate goal of European railway integration. It means a driver trained in one country can seamlessly navigate the digital cab signals of another, completely revolutionizing European logistics. No more locomotive swaps at the border, no more confusing arrays of different national signals, just one standardized, fully interoperable platform, allowing for open, competitive, and highly efficient rail transport.
Think about that for a second. If an entire continent can overcome the massive engineering, historical, and political hurdles to unify 30 diverse legacy systems into one seamless digital standard, the potential for worldwide adoption is literally incredible. It leaves us with a fascinating engineering prospect for the future of global transit, but for now, that wraps up our foundational look at this system. Thanks, you can see in next video.